everybody, this is a quick last part of chapter 5 for our inverted lecture tomorrow. And so what I'm going to go through real quickly are Fischer projections, molecules with more than one stereogenic center. I'm not going to spend a whole lot of time on the discussion of separation of enantiomers. I'll talk a little bit about some of that. And then the chiral molecules without a stereogenic center. The important thing to note there is that the only thing that makes something chiral is that if it and its mirror image are non-superimposable on one another, then you have a chiral thing. And so molecules, it's not necessary that they have a stereogenic center per se. That is a carbon with 4 different things attached to it. Molecule and its mirror images need to be non-superimposable. So I have to admit at the very beginning that Fischer projections are not my most favorite way of representing a molecule. We've learned about Newman projections. Fischer projections are kind of the same thing in the fact that we're taking a 3-dimensional object and projecting onto a 2-dimensional surface. But it is not it's not my favorite way of representing molecules, but it does have a lot of uses in terms of sugar chemistry. And so when you're in biochemistry and you're looking at the chemistry of the sugars, Fischer projections actually become quite useful in that regard. So let's take, for example, R2-chlorobutane, which looks like this. And so, so you have the ethyl group, you have the chlorine coming towards us, you have the hydrogen coming towards us, you have the ethyl group going back, and actually the methyl group is also going back. So basically, you need to think of that carbon-methyl group bond as being a dashed wedge as well. It's just not showing up that way on this particular slide. I apologize for that. So if you look at that, what you can say is that the carbon atom itself is lying in the plane of the screen, and either the substituents are coming towards us or away from us based on that projection. Now, if I take that molecule and I smash it flat, if you built a model and you imagine smashing that flat into the plane of the screen, what you get is a 2-dimensional representation of that molecule. Okay, and so what you would have then are the hydrogen and the chlorine on the horizontal line, and you would have the ethyl group and the methyl group on the vertical line. And where the 2 lines intersect at the center there, right here, is the carbon atom right here. So carbon atoms are actually the intersections of these lines, and then the groups that are attached to them are shown here. So that's what would happen if you took that. This is a Fischer projection. Okay. And there are a couple of things that you need to know about using Fischer projections. So for example, if we take 2s3r dibromobutane and we build the model, okay, you can see that this molecule is actually what is called a mesocompound. That is, it has a mirror plane of symmetry through here. These are chiral centers, but there's a mirror plane of symmetry that runs through here. And so overall, the molecule is not chiral. It is superimposable on its mirror image. And so we can imagine taking this and smashing it flat, and we would have the Fischer projection shown here. Okay, and so it works really well for showing things that have a plane of symmetry, for example. So there are a couple things that you need to remember. They only have meaning for structures with stereocenters. So if a molecule is achiral by definition, no stereocenters, I should say, then Fischer projections are totally useless. You can rotate a Fischer projection by 180 degrees in the plane of the paper, but you can't rotate it any other angle. If you rotate it 90 degrees, you actually end up with a different stereochemistry than you do if you just left it alone. Okay. Any one exchange of groups around a stereocenter produces the other configuration. So if you have R in the Fischer projection, if you switch the 2 groups on the horizontal or the vertical, you would end up with the S. Okay, and so any even number of exchanges produces the original configuration. So if I take the horizontal ones and I switch them and then I switch them again, I'm back where I started. Is basically what this is. Another thing that we need to talk a little bit about is molecules with more than one stereocenter. So if we look at this particular molecule, this is cholic acid. It's a natural product. Your body produces this. And if we look at it, we can see that there are a number of stereocenters. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 stereocenters in this particular molecule. And so there are 11 chiral centers, or stereocenters, and that means that there are 2 to the 11th possible stereoisomers for this molecule, because think about it, each stereocenter can either be R or S. So if we assembled this at random, where we didn't care whether or not the first stereocenter was RS or the second stereocenter and so on and so forth, there are 2,048 possible ways to do that combination. So you should end up with a maximum of 2,048 stereoisomers for cholic acid. And just to let you know, Mother Nature makes one and only one of these stereoisomers. Okay? And so the second one would be, of course, the enantiomer of natural cholic acid, and that would leave then 2,046 of those stereoisomers that are not mirror images of cholic acid. And when you have a molecule which is which is connected the same but is not a mirror image, then we call these things diastereomers. Okay, so one enantiomer is the cholic acid as you see it. The mirror image of that is its natural one, and all 2,046 of the remaining ones are what we call diastereomers. And it's important to note that diastereomers have different physical properties with respect to each other. They'll have different melting points, different boiling points, different spectra, etc., etc., etc. So when we're trying to determine the relationship between two molecules, we ask ourselves a couple of questions. And so this flowchart works pretty well. And so if the molecules have the same molecular formula, if the answer to that is no, then they're not isomers. They're just different molecules. If the answer to that, however, is yes, then they're going to be isomers of one another. Now, if the molecules are named the same except for prefixes such as cis and trans, R and S, if the answer to that question is no, they're constitutional isomers. Like the difference between 3-methylpentane versus 2-methylpentane. Those have very different names. Those are constitutional isomers. However, for example, R2-fluorohexane versus S2-fluorohexane, they have the same name except for this prefix business in terms of cis, trans, R, and S. And so if the answer there is yes, then they're stereoisomers. Then you ask yourself, are the molecules mirror images of one another? And if the molecules are mirror images of one another, then they're a pair of enantiomers. If the answer to that is no, then they are diastereomers. So the way that I like to think about this is my right hand is a mirror image of my left hand, and so they are enantiomers of one another. But my right hand and my right foot are not mirror images of one another. They are diastereomers. So think of it that way. So again, here's an example of some diastereomers. You need to read through this for tomorrow. So again, if you look at molecule B, right, and we look at A, where it's rotated, these are non-superimposable mirror images of one another, and so they are enantiomers. Go through that. You can go through this on your own. We've already talked a little bit about mesocompounds. Mesocompounds are molecules which have stereocenters but are overall non-superimposable. So if you look at 2,3-dibromobutane, where the two bromines are actually kind of trans to one another, if you will, and the methyl groups are cis, if I look at this and its mirror image, I'll find that they're non-superimposable, and so they are enantiomers. Notice there's no plane of symmetry within this molecule, or no inversion center. However, if we go with a group where the two bromines and the two methyl groups are kind of cis to one another, if you will, I can make a mirror image of this, but then I can take this and perfectly superimpose it on this. And so even though this molecule has stereocenters, there is a mirror plane of symmetry that runs through it, and so it's going to be superimposable on its mirror image. And so even though it has chiral centers, it is, in fact, non-chiral, and so we call this a mesocompound. So it's an achiral compound that contains tetrahedral stereogenic centers, is what's known as a mesocompound. We can separate enantiomers fairly easily these days through a variety of techniques, but one of the traditional ways is to make salts that are actually diastereomers of one another. So let's suppose we have a mixture of this 2-phenylpropanoic acid. We have a carboxylic acid. We have a chiral center here that's indicated with this asterisk. And we've got 50-50 mixture of both the R and the S stereoisomers. And so this is racemic. So how can we separate the R from the S? Well, one of the things that we can do quite easily is react this with a base that is also chiral, and we can get these from Mother Nature. These are called alkaloids. Don't worry about the structure of them at the moment. But we know that acids and bases react to give salts. And so if we think of the minus alkaloid, so this just means that it rotates plane polarized light in the negative direction. When this reacts, you will actually end up with a pair of diastereomeric salts. So you'll end up with the positive enantiomer, the one that rotates plane polarized light in the positive direction, making a salt with this minus alkaloid, so you end up with a plus-minus salt. Or you can have the minus enantiomer of the acid reacting with the minus alkaloid to make a minus-minus salt, and these are actually diastereomers. And as I mentioned before, diastereomers have different physical properties, and so we can use that then to recrystallize one of the salts and make a solid out of it, and actually isolate it and go through this whole process, and we can actually isolate one of the enantiomers. So let's say we recrystallize, and it's the negative salt that recrystallizes, it forms a solid. We can actually take that and then convert the salt back into the carboxylic acid by treating it with a strong acid. And then we could take the stuff that remained in solution that didn't crystallize out, which would be enriched in this other diastereomer, and we can do the same thing in a totally different beaker, and we can actually end up getting separation of the enantiomers that way. I'm not going to talk too much about using chiral chromatography, but that is something that we do in my research group quite frequently. It allows us to separate molecules, chiral molecules, pretty easily using chromatographic separations. I'm not going to talk about that right now. And then tomorrow we'll talk about molecules that can be chiral without chirogenic centers, or excuse me, stereogenic centers. So I'll see you all tomorrow in class. Make sure you read the rest of the chapter before coming to class. It's very important to have that information before we get started on our inverted layers.